Okay, let's start with the afternoon session with Naveen Prabhakar from ICTS, who will tell us about emergent time in Hamiltonian general relativity.
Thank you, Raju. So today I'll be talking about this topic, which was, this work was done in collaboration with Anurag Kaushal, who's a postdoc here in Spentavadia. So let me begin with some motivation. So there's this famous problem of time in general relativity, which it's more of a feature than a problem, but that's the way it's phrased, which is that general covariance implies no absolute notion of time. And let's try to understand this a bit. So given a coordinate system in 3+1 dimensional spacetime, constant time slices constitute a foliation of the spacetime. And different choices of coordinates, that is the entire coordinate system, gives a different foliation of the same spacetime. And each spatial slice in a given foliation is intrinsically the same three-dimensional space sigma, but the metric on the three-dimensional space keeps changing with each leaf of the foliation. And a given foliation can be thought of as embedding this intrinsic three-dimensional space into the four-dimensional spacetime. So I give an example of foliation of a Euclidean space. So it's not of Lorentzian signature, because it's easy to draw different kinds of foliations. So here we're looking at two different foliations of the plane. On the left, we have a foliation by straight lines which are parallel to each other. And on the right, we have a foliation by circles of different radii. And the point about embedding, we can explicitly see here that the intrinsic manifold in, say, the left foliation is always the real line with some coordinate r. And this is embedded into the plane with two functions, which specify the x and y coordinates of a point on this line this way. And on the right, similarly, the embedding functions are the usual parameterization of a circle in terms of angle and radius. And this t is the radius of the circle, right? And this motivation was to understand what is the true configuration space of general relativity. One might think that it's the full metric on the 3+1 dimensional spacetime, but since we saw that different choices of coordinate systems give us different ways of looking at the same spacetime, the more natural configuration space variables would be the metric on the three-dimensional manifold sigma, which is a 3×3 matrix, symmetric matrix. And the time evolution, which builds the spacetime for us, would be a path in the configuration space of three metrics on this three-dimensional manifold sigma. And if we count the number of degrees of freedom, there will be four functions which describe the embedding of sigma in the four-dimensional spacetime, just like we had two functions here for the two-dimensional space. And there are 6 components in the metric, which are the degrees of freedom which are present in this. And among those, 4 of them should be the embedding functions. This was realized by relativists in the 60s, Teitelbaum, Kucharz, and many others. And the remaining 2 functions, in a coarse counting way, should describe the physical degrees of freedom. And this agrees with our calculations in gravitational waves, or like small fluctuations about flat space-time, where we see the 2 polarizations of gravitational waves, or gravitons. But the point here is that it's hard to isolate the 4 embedding functions among the 6 functions in GIJ. And this is phrased as by saying that general relativity is a parameterized theory, in the sense that the parameters of the embedding into 4-dimensional spacetime of the sigma is mixed in a very complicated way with the 2 real degrees of freedom. In contrast, quantum field theory on a fixed background can be written in a parameterized form, and it can also be easily deparameterized. This was studied by Dirac, Adium, and many others. So, but still, in many applications, it's essential to deparameterize general relativity by figuring out some degree of freedom, which could come from, say, some component of GIJ here, or some function of some components of GIJ, or some internal matter degree of freedom, or empirical sources, and so on, and to interpret that as time, and studying the remaining degrees of freedom as a function of that. So in this work, we use this Einstein-Hamilton-Jacobi equation to derive a general formula for time in terms of the intrinsic 3 geometry on a given 3-dimensional manifold. And the formula looks like this. I'll come to the different terms here, or factors here in a bit. So this concrete formula, as you can see, depends on the internal degrees of freedom. where this R is, for example, the Ricci scalar curvature of the metric Gij on the three-dimensional manifold. And this acts as a guide to deparameterization. So suppose I choose my sigma and this auxiliary function n, which I will motivate in a few slides down the talk, and this cosmological. Suppose I choose everything here, then this formula tells us that this particular function of the degrees of freedom on the three-dimensional manifold will serve as a notion of time. And why is this true? It turns out that once we choose this to be time for our embedding of sigma into some four-dimensional space-time, we recover Einstein's equations for the four-dimensional metric in terms of derivatives with respect to this tau. So this, yeah. Yeah, I'll come to the description of various quantities here. This was just to flash the final result of it. Yeah. Okay, so we will take a simpler example where we can see this kind of emergent notion of time, which is in the time-independent Hamilton-Jacobi equation in classical mechanics, where this is the form of the equation, where h is some function which, if you approach this problem from a Hamiltonian point of view, is the Hamiltonian of the classical dynamical system. And this dw by dq takes the place of the momentum, the conjugate momentum. But we will take this equation as the starting point of the analysis of our dynamics, without knowing where it came from. And then we try to derive what kind of dynamics results from solutions of this equation. This w is called the Hamilton's characteristic function. And this is a function on the configuration space, which has coordinates q. At this stage, this number e is just a parameter, which will be identified with the energy of the system once we come to the final solution. So as we can see, there is no notion of time. All the derivatives are with respect to some coordinates on the configuration space, but we will recover it in the process of solving this equation. And for a concrete example, we take a particle on a Riemannian manifold M with coordinates qi and metric gij, subject to a potential function v of q. And this Hamilton-Jacobi equation turns out to be this, where this is the inverse metric. So now we consider paths in configuration space, which is this Riemannian manifold M, and we parameterize the paths by the distance s measured along the path with this metric. So to answer your question from before, the s which we saw in this formula will be the analogous distance measured with some metric defined on the configuration space of three metrics. Right, and we look, was there a question? Right, and we look for solutions of this equation such that their gradient with respect to q is along the tangent to a path in configuration space. So this is the method of characteristics of solving a partial differential equation. So we take this and then plug it into this equation here, and we get an ordinary differential equation along the curve or the path in configuration space. And this can be solved trivially to give a solution for Hamilton's characteristic function, which is this. And since the gradient of w is only along the curve, so any derivative normal to the curve is 0. This tells us that this formula for w, which is valid along the path, should be stationary under path variations, which deform the path in the normal directions. So I just implement that, and notice that we have to vary both the integrand and this measure ds prime, because this ds prime measures the distance along the path. So if we change the path a little bit, the measure also changes, and that's encoded in this derivative. So all this can be worked out explicitly given these expressions for the metric and so on. And then this turns out to be the equation which we have to set to 0 to ensure that this is stationary under path variations. And we'll present the result for flat space where this m is some positive number. And then it turns out that the equation, after you plug in this quantity here, takes the suggestive form, where you see that the derivative with respect to the path parameter always is accompanied by this combination of the quantities defined on configuration space. Where this is the parameter E, which now with our classical mechanics background, we can identify with energy, and V is the potential along the path. And this is the derivative of the potential. So we define a new parameter tau along the path through this. And as you can see, this equation just reduces to the usual equation of motion for a particle traveling in flat space subject to a potential, which is nothing but Newton's law. So this calling this tau time agrees with our usual notion of absolute time, which we write down for classical mechanics. So we will see an analog of this phenomenon happening in general relativity as well, which motivates us to call that tau which emerges from the configuration space or geometry of configuration space as some kind of deparameterized time for GR. Yeah. I just, for simplicity, I take it to be flat. Yeah. Otherwise, what happens is we'll get some extra Christoffel symbols here, which is basically the geodesic equation with a force term. But just to make the point, in as simple a situation as possible, I chose the flat metric. Right. Yes, exactly. Yeah. Right. So even in GR, we will see that we have to input a metric like that.
I have a question. Yeah. I didn't get the part about setting delta W to 0. Sorry, I'm not very familiar with this formalism.
Yeah.
So you first have a differential equation for W that you solve, and you get one. Yeah, you got some answer in the next here in the first line. Then what is happening with the variation?
Right. So this solution for W was such that its change in configuration space was only along the path. So the gradient of W, as you can see, which is a vector, which is in general, it can be zero in any direction, non-zero in any direction in configuration space, is restricted to be along the tangent vector to the path, which implies that W does not change when you deform it along the normal. Along a given path, which will turn out, so we're going to get a consistent equation for that path. So we write down a path and then demand that that path satisfies some equation. And that equation is obtained by implementing this variational procedure, and that's the equation for the path. So at the beginning, we say that we assume the existence of such a path, along which the gradient, such that the gradient of W is only non-zero along that. And then it turns out that it's not valid for any arbitrary path in configuration space, but the path has to satisfy a constraint, which is this equation. Yeah. Right. So I just want to make one point, which will be important in generalizing this to GR, which is that the previous derivation was valid for V, the potential less than E, all along this assumed path, for the square root to make sense. But the paths with V greater than E are important for semi-classical tunneling. For example, instanton solutions which interpolate between vacua, where this parameter E is set to 0. And there is an analogous Hamilton-Jacobi equation which can be, for example, derived from the Schrodinger equation in the WKB approximation of this kind. And this gives rise to this Wick-rotated version of the Hamilton-Jacobi equation we wrote down earlier, where the sign of this first term is flipped. And we have set E to 0 because in this simple example, we want to look at a tunneling solution between vacuum, different vacua of this potential. And the same procedure, now given a partial differential equation of this kind and a metric on configuration space, etc., we can repeat the same procedure and we will get the same notion of time with some obvious changes in, what is that? Here, some obvious changes that this V minus E must become, E minus V will become V minus E and so on. And tau now becomes a notion of time of flight for this instanton solution, which measures in some sense the notion of time between, from the beginning of the instanton, from one vacuum, to the ending of the instanton solution at the other vacuum. And similarly, there will be an equation just like this, but with the opposite sign for this force. So the idea is for a semi-classical tunneling path, there can be a priori no notion of absolute time, because it happens in a forbidden region, classically forbidden region. But this procedure still gives a parameter to describe the development of the instanton from one vacuum to the other. And in this sense, from the configuration space, a notion of time emerges, even though classically there was no motivation to consider any notion like that. So in general relativity, we would like to take this idea and implement with an analogous Hamilton-Jacobi equation. Yes, but you could have said that one derived this Hamilton-Jacobi equation from a formalism which had some time to begin with, like in the Lagrangian or something. But for the tunneling solutions, even that was not available because it was classically forbidden. But even then, we had a notion of the Hamilton-Jacobi equation from which this parameter came out. So for GR, we start with the three-dimensional manifold sigma of Euclidean signature, which will be a spatial slice eventually in the four-dimensional space-time. And the configuration space, which I call as N sigma, is the space of Riemannian metrics on sigma. And Hamilton's principal function, or characteristic function, doesn't make a difference here, will be a functional on this configuration space. And the Einstein-Hamilton-Jacobi equations are these. So this looks very similar to the equation that we had here, where W is replaced by this S, and this metric is replaced by this GIJKL, which can be thought of as a metric on these partial derivatives, and so on. And this combination serves as some kind of a potential energy for the 3 metric. And there are these other 3 equations where J goes from 1 to 3, which are there in addition to this kind of equation because of diffeomorphism invariance, or rather a choice of coordinates on this 3-manifold sigma. And these equations, for example, can be derived from the Wheeler-DeWitt equation in the WKB approximation, just like I mentioned that this equation could be derived from the Schrodinger equation in the WKB approximation. So let's focus on the last 3 equations first. These imply 3 diffeomorphism invariance, that is invariance under a choice of coordinates on the 3-dimensional manifold sigma of this principal function S, which can be seen by the simple manipulation. You just contract this equation by a vector field Zj. If sigma is non-compact or has boundaries, then this has to vanish on the boundaries. These are the small 3 diffeomorphisms. We can do a partial integration, and this is basically the transformation of S under a 3 diffeomorphism of the metric. And what this says is that this S should be a function in the space of 3 geometries rather than 3 metrics. So now let's focus on this remaining equation, which looks like this Hamilton-Jacobi equation of classical mechanics. And this GIJKL, it is part of the input of this theory, which, for example, can be derived from Wheeler-DeWitt, but at this, for us, this will be the starting point. So we just take this on face value. And this has this particular formula, which, as you can see, is local on sigma on the 3-dimensional manifold. This entire equation is a local equation on the 3-dimensional manifold, and all these indices are contracted. Right. So instead of one Hamilton-Jacobi equation, which we had for classical mechanics, we have an infinite number of these corresponding to every point on sigma. So to apply the same techniques as earlier, we want to get one equation from all this, but still we want to keep this local dependence in some sense. So what we do is smear that local Einstein-Hamilton-Jacobi equation with a positive function n of x on sigma. So at this stage, this is just some arbitrary function such that it should never become 0 on sigma. And so there is, we still have retained this local dependence because we can choose this n, for example, to be some delta function focused. I mean, it will not satisfy this positivity condition, but we can think of it as a limit of positive functions, for instance, and recover the local equation again. So we will be working with the smeared Einstein-Hamilton-Jacobi equation. And as in the classical mechanics case, we will consider a path in the configuration space of all metrics. So there is an additional parameter S. So these x's are coordinates on the 3-dimensional manifold, and this S is the path parameter. So I take configuration space, which is some infinite dimensional space, and then I consider a path. And this path is parameterized by S, which is the distance measured with respect to a metric, which I'm going to write in a bit, from some starting point in the configuration space to the point where we want to look at. Again, we will look for solutions of this equation such that the gradient of this principal function is only along the tangent direction to such a path. The tangent direction is basically the derivative of the metric Gij with respect to the path parameter. As a metric, it does. In the next slide, I'll discuss that. So this is another difference from the usual Riemannian manifold, particle on Riemannian manifold, and it's important in GR as well. That's right. So it's very hard to implement this constraint at the outset, these constraints. What I do is implement these as Lagrange multipliers in my solution. So it is part of the story, but it is easier to work with 3 metrics and then impose this with a Lagrange multiplier. Good points. I'll come to all that in the rest of the talk. Right. Yeah. So where was I? Right. Yeah, here. So this inverse of this GIJKL is called the DeWitt metric. So GIJKL has to be thought of as a metric with ij as a pair of, as one collective index and kl as another collective index, so that it serves as a metric on configuration space of GIJs. And one can take an inverse in that sense, and this will turn out to be a formula. So this GIJKL will satisfy something like GIJKL, GKL, AB is half delta I A and the sum is over K and L. One can check that this satisfies that given this GIJKL this form. And this suggests a natural metric on the configuration space where you just contract to arbitrary variations with these indices. And it has indefinite signature, as Sandip pointed out, due to this conformal mode of this metric. So I split the metric into two factors. One is this overall scaling factor and another factor G twiddle, which has determinant 1. And one can plug this back in here and here. And this expansion turns out to be like this. And as you can clearly see, there is an additional minus sign in front of variations in the conformal mode when compared to the variations in the others. Right. And these constants are dimension dependent. I've looked at 3-dimensional manifolds, so we get 32. Right. And this slide I already discussed. So now, now that we have talked about this metric, recall that we smeared the Einstein-Hamilton-Jacobi equation. So from the smeared equation, we can extract a metric which has an additional n in it, this unknown positive function or unfixed positive function. And we can write down a smeared Dewitt metric on configuration space, which is the stuff inside this absolute value. But now, as we just saw, this can be negative, positive, or 0. So we would like to parameterize our paths with the absolute value of this metric. And we would like to focus on those situations where along a small part of the path, or rather we choose paths which are small enough such that the sign of ds square, rather the quantity inside the absolute value, has the same sign and is non-zero. If it is 0, we cannot proceed with this formalism because you see all kinds of derivatives with respect to ds, and it's singular when ds is 0. So we work in this general situation where ds square is non-zero. Right. And there's one extra ingredient, which is that the tangent vector to the path, just this, must be orthogonal to deformations in the configuration space, which are generated by spatial diffeomorphisms. So there could be delta Gijs which look like that arising from a diffeomorphism on sigma. We don't want to consider such tangent vectors. And this was actually encoded by the other 3 equations, which was part of the Einstein-Hamilton-Jacobi equations. And this we can say, we can encode by saying that the tangent vector dgkl by ds is orthogonal to all diffeomorphisms with respect to the smeared Dewitt metric. And since this should hold for all zj, this gives rise to a local equation, which is this. And this we implement by a Lagrange multiplier this way. And this was the formula for S, which we will get if we follow the path, the procedure which we did in classical mechanics. So there is a subtlety about these equations, which I would like to spend a few minutes on, because this is a very strong, this feature is unique to GR in all the field theories that one studies, classical field theories one studies. And the subtlety is due to the indefiniteness of the smeared Dewitt metric. And the subtlety is that orthogonality with respect to the smeared Dewitt metric does not imply transversality. So the real statement would be that tangent vectors along physical paths should be transverse to deformations which are generated by diffeomorphisms. And when the metric on configuration space is positive definite, this transversality can be replaced with orthogonality with respect to that metric. But if it's not positive definite, then orthogonal does not always imply transversal. In particular, there can be 0 modes of this above equation here, which are not just killing vectors, for example, which will satisfy this equal to 0, or just z equal to 0. If this Gijkl were positive definite, then the only solution to this equation would have been z equal to 0, or killing vectors if they are present. But because Gijk, that can be seen by a similar argument to what I did earlier here. So you just multiply or contract this equation with Zj, which is the free index, and then partially integrate and integrate over sigma. Then you get a positive definite object and set it to 0. So that just sets the this itself to 0. So we get the killing equation that way. But that cannot be done here because this Gijkl is negative definite. So this implies that if there are non-trivial solutions to this equation, then there are diffeomorphisms which are orthogonal to all diffeomorphisms. They are null with respect to this smear-Dewitt metric. As I mentioned, Killing vectors are trivially solutions of this, but there can be more non-trivial solutions, which I will discuss in a bit. So the presence and number of zero modes of this equation depend on the three-dimensional manifold that one starts with, and the choice of the metric on the three-dimensional manifold, and the smearing function n. Clearly, I mean, all of those go into this equation. So we should at least expect some dependence on these. And the number of zero modes is actually related to the thin sandwich conjecture, which I will not go into. So let me give a few examples, just to make everyone comfortable with this point. So suppose we take the smearing function to be 1 everywhere on sigma, which is a good choice because it's positive everywhere. So one example is to take sigma to be an open region in any three-dimensional manifold, and the metric to be flat in that region, or Euclidean in that region. And then one can see by just plugging in these inputs to this equation, there are an infinite number of zero modes which are parameterized by compactly supported functions on this open region. So there are gradients of this compactly supported function, and if one plugs in that expression for xi here and all the remaining things for gij equal to delta ij and so on, then we see that this equation is automatically satisfied. These are diffeomorphisms. Yeah. But these are orthogonal to all diffeomorphisms. So if one is not careful, one would interpret those as, or use those as physical tangent directions. In fact, there are some solutions which are these Kastner metrics, which are generated by such null diffeomorphisms, by a particular choice of this function phi. So it's not clear whether these null diffeomorphisms are physical or not. They have to be treated separately. And example 2, where there are no zero modes, is when sigma is closed. It's compact without boundary. And gij is a metric with negative definite Ricci tensor everywhere on sigma. Then again, an analysis of this equation will show that there can be no solutions other than 0. And usually when you have a negatively curved space, you don't have Killing vectors either. And for the third example, there are no zero modes when sigma, along with a given metric, is an Einstein space with positive Einstein constant, which is something like this. In which case, the only solutions to the zero mode equations are Killing vectors. And the indefiniteness of the metric was caused by the presence of the deformations along the conformal factor of gij. So another way to kind of cure these, the existence or this subtlety here is to freeze out deformations along the conformal factor along the path, which is to which is the statement that the determinant of the 3 metric along the path is constant. And this is given by saying, this translates to saying that the tangent vector is traceless with respect to this gij at every point on this path. And this automatically will kill this additional component in the Dewitt metric, and the remaining part is positive definite along the path. And in that case, the analysis of this equation was, as I had outlined a little bit earlier, which is that because this is positive definite along the path, the only solutions will be Killing vectors of 0. Yes. Yeah, I mean, and it's also not clear whether this can be imposed on paths at all, given a choice of sigma. And this is called the maximal slicing condition or the zero mean curvature condition, because it turns out that the local volume, which is measured by this determinant, or square root of the determinant, is extremized by this above condition. And in Lorentzian signature, in the space-time, this is a local maximum. And so one has to figure out whether one can impose this consistently along the paths. And it turns out it can be done in many situations, for example, asymptotically ADS spacetimes, where one has to do an analysis of the Hamiltonian constraint. I'm jumping ahead, but this is the, so there is some non-trivial calculation that goes into checking whether this condition can be imposed along the path. But if that is possible, then these zero modes are no longer a problem. Okay, so let me come back to the main thread of the talk. So we start with this expression S, which has this this integrand, which came from this Hamilton-Jacobi equation, this one. This is just the square root of what appears here is just the square root of the potential. And this is the diffeomorphism constraint implemented with the Lagrange multiplier. So there are 3 fields here, which is Gij, N, and Nj. And then we have to extremize with respect to all these by the same rationale we used for in classical mechanics, that we were looking for solutions of the Hamilton-Jacobi equation where the gradient of this principal function was non-zero only along the path, so that any normal deformation along the path will leave this function invariant. So these stationarity equations will eventually give rise to a notion of time, which looks like this. So ds now is the path distance measured with respect to the smeared divot metric, which I wrote here. The rest of the quantities here are quite standard. So n is this smearing function, and then r is the Ricci curvature of Ricci scalar of the three-dimensional metric, and then lambda is some constant which will be interpreted as the cosmological constant of the four-dimensional space. That can be seen immediately by looking at the equations of motion with the analog of Newton's law, which we will get when we set the delta is equal to 0, which are basically the 10 Einstein's equations. And this lambda will take the place of the cosmological constant there. And these equations are written naturally in terms of this combination of the tangent vector. So there is a partial GAB which is missing here. Sorry for that. So you subtract a diffeomorphism due to this Lagrange multiplier here. And you get this quantity KAB, which you identify as the extrinsic curvature of this embedded three-dimensional manifold in four-dimensional space-time. And the extremization equations are basically these. So the first one follows from extremizing with respect to delta n. Second one follows from extremization with respect to this Lagrange multiplier. And the third one is follows from extremizing with respect to Gij. So as I was saying at the beginning of the talk, if one sees these equations, so this is another equation which can be thought of as an equation for GAB. So these are first order equations. Notice that this parameter tau defined this way appears in the usual place of time that one writes down for Einstein's equations. So this notion of time that one usually takes as some kind of a coordinate in a four-dimensional space-time emerges from the geometry of configuration space. That was the main point of this work. And as I mentioned, these above equations are precisely the Einstein's equations for the space-time metric written in ADM form, which is this, where you can see that all these smearing functions and the Lagrange multipliers take the usual roles of the lapse and the shift respectively. And this parameter tau serves as the time coordinate for this ADM split of a four-dimensional space-time. So the lesson or the message of this calculation is that the extremal path in configuration space, which is basically a path such that the gradient of the Hamilton's principal function is non-zero only along the path, describes the four-dimensional space-time geometry such that where at each point of the path, I have one leaf of the foliation in 4 dimensions. And it's equipped with an intrinsic time parameter that depends only on the 3 geometry on the path of that sigma at each point of the path. And some auxiliary parameters, which are these lapse and shifts. Right. So there are extensions. So, so far I assume that in all these manipulations where we extremize, there are some partial derivatives which gives rise to boundary terms. I've assumed that all of them are 0 or can be set to 0. So they are 0 automatically when sigma is a compact manifold without boundary. But this procedure can be extended to the situations where sigma has boundaries or asymptotic regions. In which case, these boundary terms in the variation of this formula for the principal function, this formula, have to be dealt with in some way by imposing appropriate boundary conditions on the fields that appear in the formula. In particular, when you have asymptotic regions, sometimes just boundary conditions is not sufficient to get rid of all the boundary terms. So one has to modify the original solution, or going back even further, the smeared Einstein-Hamilton-Jacobi equation with some surface terms, or the boundary terms, depending on the boundary of sigma. So for example, if you take asymptotically flat spacetimes, imposing these Rejet-Teitelbaum fall-off conditions, reproduce the definition of ADM energy in this setup. And one may also wonder whether this, for non-compact sigma, whether this integral makes sense because it could be divergent. In that case, we may have to find correct counter terms to cancel the divergences. And we can also add sources and matter couplings which modify the smeared Einstein-Hamilton-Jacobi equation, and in turn will modify the denominator here with additional terms, which are basically the T00 components of the matter or the sources. And this will in turn modify the time formula here with additional terms. We'll come to an example in a bit. And further, because this formalism is so general, we can also, and it only depended on paths and configuration space of metrics on a 3-manifold, one can also describe Euclidean evolution. Because the signature of the eventual space-time we construct is not clear from this construction. And it turns out that to realize Euclidean time evolution, one has to flip the sign in the first term of the Einstein-Hamilton-Jacobi equation, which is this term here. So this is reminiscent of the instant-on tunneling situation in classical mechanics. So there's some kind of Wick rotation. I missed one formula here, which is that finally when we plug all this in, one can also rewrite this in terms of the conjugate momentum of Gij. We'll get the Hamilton equations of motion. And the conjugate momentum pi ij can be identified with this functional derivative of S, which is again a standard formula in Hamilton-Jacobi theory. And this Wick rotation is basically taking pi ij to I or minus I pi ij, depending on the kind of analytic continuation we want to do. And that reproduces an additional sign here. In particular, that also corresponds to flipping the sign of this quantity on the left-hand side. Right. So I just want to point out one point here, which is this additional sign that results from this kind of Wick rotation for Euclidean solutions can also be realized by taking a choice of Gij such that its sign changes this intrinsic quantity computed from the geometry on sigma. So this leads us to wonder whether there can be a path in configuration space such that for some sections it describes a Lorentzian evolution in space-time, and there is a transition to a Euclidean evolution where the sign of this quantity changes. That's just speculation, but it will be nice to see such, if such an interpretation is possible for this equation. Right. So let's look at an example of this computation. So one can do a systematic study of paths in configuration space by organizing them with symmetries of metrics that we take on the 3-dimensional manifold. By the way, all this formalism can be extended to any spatial dimension D, as long as that D is greater than 2. And so this configuration space can be stratified into submanifolds which possess a particular degree of symmetry, which is the number of Killing vectors of the metrics that are present in that region of configuration space. So as usual, we try to begin with the most simplest situation, which is that of maximal symmetry in 3 dimensions. The possible groups are at least locally, so without worrying about discrete quotients, are SO4, SO3, 1, and the Euclidean Poincare group, which is SO3. The corresponding spaces sigma are the 3-sphere, the 3 hyperbolic space, and Euclidean space R3. We also choose this cosmological constant lambda to be positive and parameterize it in the standard way in terms of a length parameter. So now let's try to look at the realization of this formula here. So we take sigma to be the 3-sphere, and maximal symmetry restricts the metric on sigma to be proportional to the round metric on S3. And there's just a radius which is free to change. So along a path in configuration, that some region of configuration space where maximal symmetry is preserved, only this radius can change. So if I take a path in the configuration space and look at the metric along the path, the only path dependence can be, only this can depend on the path parameter S. The smeared divot metric without the, smeared divot metric along the path is negative because this is essentially the conformal mode of the metric. And the integral along sigma is trivial because nothing depends on the angles of S3, and you just get some measure factor, some volume of S3. And this is it. So the path length parameter is the absolute value of this, and it's given in terms of this conformal mode to be this. Right. So this is the first ingredient of the time formula, which had ds in the numerator, if you remember. So the other part is the denominator, and that can be computed. I'm not showing the computation here. So that can be computed by taking this formula for Gij, plugging it into the Ricci scalar, etc., and then computing that. And what we get is this quantity, the simple quantity. And then this can be integrated trivially to get this formula for tau in terms of a particular mode of the 3 metric. This is the kind of formula that we were looking for at the beginning to deparameterize GR. Yeah, it does. Over the paths in configuration space, yeah. I mean, there always is a path. It's not just at one point in configuration space where tau emerges. Right, that's what this formula is telling us, right? Right, but the integral is an indefinite integral from an initial point to some variable final point. So I start with some putative initial point, and then I look at how this path is parameterized with respect to that special parameter tau. And at each point on the path, I get a formula for that time in terms of the configuration space variables present at that point only in the path. So for large A, this simplifies, and what we get is the log of the volume of the 3-sphere at that particular value of the conformal factor. So as we can see, so this is the usual Misner time, or so I don't know who first proposed it, which is that in an expanding universe where the volume monotonically increases or changes, one can imagine making local measurements on the three-dimensional manifold and coming up with a formula for time. Will break down, yeah. So you can either do it for the past or for the future visitor. And the formula picks out this constant conformal mode of Gij as a notion of time here. So this is a very symmetric situation where we could do all these calculations explicitly, but the message still is still present in more complicated situations. For example, if we look at fluctuations of the metric about this background, which need not respect any kind of symmetry. And just for completeness, if we take the other two maximal symmetries, we will get the well-known flat and hyperbolic slicings of digital spacetime. We can also plug this back into the ADM-like formula and then get the usual four-dimensional metric for de Sitter. I'm not exhibiting here. And then we can also imagine coupling metric to the metric on sigma to some matter degrees of freedom. For example, in models of inflation, people usually look at minimal coupling of a scalar field to the metric. The scalar field contributes to the Einstein-Hamilton-Jacobi this way. So there is an additional contribution, which again is essentially the T00 component of the stress tensor. And suppose we still work in a maximal symmetric situation, where it implies that the scalar field is constant on S3. So it's only dependent, the magnitude of the scalar field is dependent only on where we are on the path, but not where we are on the spatial manifold. The appropriate formula for d tau comes out to be this. So as we can see, the configuration space metric now has two parts. One is the original part, which came from the conformal mode of the 3 metric, and now there is a contribution due to the scalar field, the constant mode of the scalar field. So the infinite dimensional nature of the configuration space has been drastically reduced to just a two-dimensional space, which is made up of A and phi. And the metric on that configuration space has Lorentzian signature. And along a particular path, we demand that the sign of that metric stays constant for the analysis to go through. So it could be inside the light cone. So it could be a time-like path in this configuration space of metrics. So it could be something here or a path here for the analysis that we just did to go through. And the sign of the numerator is related to the sign of the denominator by the Einstein-Hamilton-Jacobi equation, such that this d tau square is always positive. Yeah. That will be one particular path in the configuration space. But there might be something else that you might be interested in, where, for example, A is fixed on the entire path, but phi changes. So then tau would be like phi, or some integral of this d phi over u of phi. Right. So for instance, if I can just pull out a dA square out of this, and then I get this quantity a square d phi over dA whole square, which is the square of this object. And if this is very small, this basically tells us that for large changes in A, the scalar field remains approximately constant. Then this reduces to the previous calculation, where this term can be ignored in favor of this. And then u of phi, because the scalar field does not change too much along the path, is approximately constant. And that gives rise to some kind of a cosmological constant here. And then this evolution would be approximately de Sitter. So these are conditions which are some necessary conditions for slow roll inflation. There's another condition which comes from looking at the Einstein equation, this one, which also tells us that the second derivative of the potential has to be small enough for the evolution to be approximately de Sitter. Right. So one can now imagine looking at this background and doing fluctuations in the conformal mode and the scalar field, and then appropriately this formula will change. And then there will be an interpretation of time in terms of some gauge invariant, the diffeomorphism invariant combination of those fluctuations. And this will give rise to some notion of time during this inflationary era, which depends on the magnitude and other properties of the fluctuations of the inflaton, for instance. Right. So finally, I'm good on time, right? Okay.
So you could choose how to go along A or phi and so on, but the maximal slicing, that equation you had,
Which one?
Theta is ds over square root of.
That's
some analog here with the
this one.
Also coming.
Yes, that's what I was saying. So it will just get this additional contribution here. Right. Yeah. Like here, I mean, there's a path here.
No condition is imposed on that path by the requirement. You're choosing rather special slices. Or am I missing it?
No, the slices are chosen with respect to this maximal symmetry. That's the only input I have. But you can relax that, because the formalism will go through. The formulas, all the formulas will go through, but they'll not be so explicit and tractable. But other than maximal symmetry, there is no other imposition on the slicing so far. So the paths that one considers in this configuration space of metrics, which has now just two numbers, two coordinates. So as I was explaining earlier, these paths cannot be arbitrary. They have to satisfy the equation of motion. So there is that one constraint, which does not appear here. So this formula also has to be solved in conjunction with some of these equations. Just like in classical mechanics, we assumed the existence of this path, finally derived an equation for that path, which was Newton's law. So, I mean, I guess this constructive approach will, the way one goes about doing this is postulate a path. I mean, give some d phi over dA at each point along the path, and then plug that back into the equations, and then check whether the equations have a consistent solution for that choice of d phi over dA. So for instance, this condition is not sufficient to ensure a solution. There could be other conditions which come from demanding that the equations of motion be satisfied for a particular path in this space. It's not even clear whether such a path always stays within the light cone or outside the light cone. Its signature, the norm squared of the tangent vector to the path can become 0 at some point, in which case this path kind of touches the light cone, or it can come back or it can go through. So there's a lot of freedom in working with this kind of situation. Then just trying to understand the equations of motion, or the kind of paths that are allowed. But whatever paths are allowed, we are guaranteed that a notion of time along the path exists from this formula. So that's the message of this calculation. Right. So now, like I said, there is another way to handle these subtle features of this Debit metric. which is to take maximal slicing, rather, which means that the trace of the tangent vector is 0. And this covariant form of the tangent vector was this Kij, which involved the tangent vector, and then there's some subtraction, which is basically a diffeomorphism with respect to the shift parameter. So one can now work in a slicing like that. So we have shifted gears, and we are not looking at symmetries anymore in the configuration space of matrix, but we are trying to construct paths such that the tangents are restricted. So the tangent space at a particular point on the path is again some infinite dimensional space. We are trying to restrict the tangent vector to be in a subspace in that tangent space such that it's traceless. And it turns out that it's always possible, for instance, to choose paths in this situation, choose paths which satisfy this condition. In a situation where you take the three-dimensional manifold to be R3, and you impose asymptotically anti-de Sitter boundary conditions on these fields that enter in the calculation. As I mentioned earlier, the conformal mode is frozen, and the smeared divot metric along this path is positive definite, because we have frozen the conformal mode. And in this case, the parameter tau serves as a global time coordinate in these asymptotically ADS spacetimes. These theorems by Crucial and Galloway and was also looked at by Witten in a recent paper, and many other relativists tells us that such slicings are always possible when you impose these asymptotically anti-de Sitter boundary conditions under some reasonable assumptions about the occurrence of singularities in the spacetime. So this includes black hole spacetimes, for example, and it turns out that these maximal slices cut across the horizon. There is a choice of maximal slicing where the slices cut across the horizon, and the corresponding Hamiltonian, which evolves the degrees of freedom in spacetime, can describe infalling observers, because the spatial slices are always everywhere. They are supported even inside the horizon. Yes, it does. Yeah, it doesn't reach the singularity because of this maximal volume condition. The singularity, if it's so that's this point, that if singularities are always of the volume crunching kind, then they will be always avoided by these maximal slices, because these slices tend to maximize volume, whereas the singularity tries to minimize volume. Right. And the time variable which we constructed here, tau, will can correspond to some kind of notion of infalling time in the dual CFT. There's some work in progress. So I'll stop here. If there are any questions or comments.
Yeah. Because it's some integral. So, I mean, once you've done that, then you've almost solved the problem of the interior, right?
Yeah.
So I am confused about how this will help you go from outside to inside.
Well, now we can look at excitations about this. Let's say we look at a probe scalar field in this background and look at excitations, which are kind of localized in the exterior to begin with. When we look at its evolution with respect to this time parameter, there'll be some sharp time beyond at which that excitation, that localized excitation, will cross the horizon. There might be a dual CFT statement for that.
But to write down this Hamiltonian, won't you need some degrees of freedom from inside the horizon? It's some integral over the slice, right?
Yeah.
And some part of the slice is already inside the horizon.
It's already inside.
So you'll need to know how that part is represented in the CFT.
Yeah.
But once you know that, then you've already solved the problem of the interior.
Right. That's in a sense true, because I mean, this particular example we are working with is this maximally extended BTZ black hole, where we already have a representation for the interior degrees of freedom from the left copy of the CFT. And then that way we have a, yeah, you're right. So there is a description of infalling observers in terms of both sets of degrees of freedom in the CFT.
Of, as we were discussing, is to make sure not to use the naive thing, which is just left plus right. Yeah. You have to use left addressed to the right.
Otherwise
right.
You'll get the that point, it would be great to discuss that point further. Just to mention, I mean, the dressing is to ensure diffeomorphism invariance in the bulk, right? But if
have the correct 2-point function, have the correct stress tensor. Otherwise, if you use left plus right, you do a diffeomorphism, you'll get you'll get the wrong answer.
But what if I dress some of the operators which are, say, present in the interior to the left boundary, and the operators which are present in the exterior to the right boundary?
Then if you look at a slightly different state, if you do a diffeomorphism, that it'll predict for you that diffeomorphism produces firewalls, because at the point where you start dressing from left to right, you'll get a kink.
So talking about large diffeomorphism.
Any large diffeomorphism, which it shouldn't. Large diffeomorphism shouldn't do anything to the geometry. So I mean, that was the original idea of HKLL, but I mean, that's not correct, I think, to just use left and right.
I mean, just to raise the point, I mean, it will be great to discuss later, but these large diffeomorphisms that we define in the CFT, if you want to continue them into the bulk, don't they already have some kind of ending in the middle, somewhere like, say, at the bifurcation point?
No, this is large diff.
Symmetry.
So there's no bifurcation point. All the small diffs are gauge. So you can always take the large diff and smoothen it out. All you know is how the large diff behaves at the two boundaries. So you can always...
The smoothing function will have a singularity at the bifurcation point because we are taking a kink and smoothing it out.
No. Why? Any diffeomorphism is a representation of that. All I'm telling you is how the boundaries behave.
Right. No, I agree that if you start with the diffeomorphism, which continues smoothly into the interior, that works out. But if I already have a prescription to continue it, say, using the killing vector in the interior.
But why? I mean, why would you use that? All you know about the diff is how it behaves outside. You don't know how it
From the ADS-CFT correspondence, there's a symmetry in the bulk and a symmetry in the boundary.
In ADS-CFT,
the action of the symmetry, which is the large diffeomorphism, continues with the
we can discuss later, but I think this is, I mean, it's pretty clear. I think that these time-shifted thermofield states don't have firewalls. So if you, this left plus right would predict that the time-shifted thermofield states have firewalls, which is, I think, physically a wrong statement. So I think that, I mean, we can discuss more.
Sure, yeah. Great, thanks.
Are you doing the following? Let's forget
the mic's probably not on.
Let's forget black hole horizons and all. We can just do your simple examples of cosmology if you like. But are you doing the following? Given a solution to Einstein's equation, because I think you were using that, but you can correct me. Given a solutions to Einstein's equations, you are asking how to find a description of the space-time which admits a foliation in the cases where it does. Is that what you're doing, or in other words, let me ask it even more dumbly.
Okay.
Suppose I find a solution to Einstein's equations. Normally I work in a coordinate system.
Right.
Okay, so I'll use some coordinate system. I can cast it in ADM like gauge if you like. And then I get some geometry and I can ask, okay, are the coordinates system I'm using, is the coordinate system I'm using foliating space-time? Yes. And then I have to check and so on. Here, you're starting the other way around, starting from solutions and trying to find coordinates, because starting from solutions, or at least assuming that you have a solution.
Yeah, assuming we have a solution.
Assuming you have a solution, then ask for that solution how you would have a coordinate system which would result in a foliated space.
That's right.
Is that right?
That's right. I mean, since we make very minimal assumptions about the existence of the solution, in the sense that this is an exploration in the configuration space of metrics, where we try to classify paths which eventually satisfy the Einstein's equations and so on. But the starting point will not be so restrictive as to guarantee manifestly that it's some solution of Einstein's equations. So there will be more other guiding principles like symmetries, for example, or the maximal slicing condition, or some other condition like that. So it gives us some freedom in exploring the solution space of Einstein's equations this way. For example, there's this Hamilton-Jacobi approach to inflation, where you can choose some function for the Hubble parameter, and then that gives you the appropriate inflationary potential. Then you can play around with the parameters there and see if it satisfies low roll or a large field or whatever like that. So it's more along that spirit, that there is some freedom in the initial choice of path in the configuration space. Then you kind of keep restricting it by imposing symmetries or other guiding principles. And in that subspace of the configuration space of metrics, or the space of paths in the configuration space of metrics, you try to explore what this notion of time means and so on. But it is true that finally what I would like is a solution of Einstein's equations. There is also the question of some quantization based on semi-classical paths. That I don't know how to extend this formalism to that, but one can imagine trying to look at quantum fluctuations about a classical solution described this way, or arrived at this way.
Okay, maybe let's thank Naveen again.